to another session of virtual classes of science here, in which we are going to see the importance and the role of dielectrics or dielectric material when it is introduced to the capacitors. And when you call a capacitor a very good capacitor or it has got a very good capacity. This is all what we are going to learn in this session. Okay. So here is capacitance and capacity. We all have seen what is the capacity, which is C is equal to Q by V, or we say that capacitance of a device is the ability of the device to store electric charge. So when you call the capacitance has got a very good capacity in turn, we say that whenever the material has got the ability to store electric charge at the least value of potential. That means when Q increases for a given value of V, we say that the capacity has got a very high value. And for a parallel plate capacitor, the value of capacitance is epsilon 0 A divided by D. Let's see how to get this expression, that is the capacity of a device in terms of its area and the distance between the plates. For that, we should know what is meant by a parallel plate capacitor. Parallel plate capacitor. As the name suggests, parallel plate capacitor is composed of two metallic plates. So each has got an area of cross section of A and they are separated by D. And for the simplest case, we are assuming that the medium between the plates is vacuum, or we can say air, with a permittivity of epsilon 0. Let us assume that this is positively charged plate plus Q and this is negatively charged plate minus Q. And for any plate, we can define the charge density. What is the charge density of the plate? The charge density is defined as the charge divided by area, which is sigma of the parallel plate capacitor. Each one has got this surface charge density. So our aim is to get the capacity. What is capacity? Capacity is Q divided by V. So in order to derive the expression for the capacity, what we should get is, we have to get the expression for Q and we have to get the expression for V. So what is Q? From this I can directly write the charge content Q on the plate can be written as sigma times A, where sigma is the surface charge density and A is the area of the plates. And that is same for both the plates. Now our aim is to get the potential, or V, potential difference between the plates. Potential difference between the plates. We call it as V. And here we have two plates, one charged to say plus sigma and other one has got minus sigma. This is a problem that we used to do for plates, which is an application of Gauss's theorem. And as per Gauss's theorem, we know that electric field due to any charged plate or any plate of infinite length, infinite area, is equal to sigma divided by 2 epsilon 0. For that is a positive plate. We can consider three areas over here, one outside the plate, two in between the plates, and three outside, that is towards the right of the negative plate. Let us look at the directions of the electric field. Due to the plus charge, we know that electric field is propagating in the outward directions. So in this direction, I can draw that one like this. This will be the directions. And due to the negative plate, what will be the electric field? That is moving into the negative plate, or I will mark it as with the negative direction. So the direction of the electric field will be like this. Here also like this. So what will be the net electric field at the point 1? At the point 1, we can say the net electric field will be, this is sigma by 2 epsilon 0 towards the left, and this is sigma by 2 epsilon 0 towards the right. Equal and opposites will give you 0 value. What about the third point? This is also one towards the right and one towards the left. That is also equal to 0. So outside the parallel plates, the electric field is 0. What about in between the plates? That is the area where we are concerned, or we say that that is the area which is enclosed by the parallel plate capacitor. What happens? One is towards the right, other one is also towards the right. What happens for the electric field? Sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, the value will be sigma by epsilon 0. We have found the electric field between the parallel plate capacitor as sigma by epsilon 0. That is the value of electric field. So we got the magnitude of the electric field, which is sigma by epsilon 0. Now our aim is to get the potential difference. And we all know that the potential difference is what? We can find it as in negative integral of E dot dr. Leaving all the negative factors and the directions, because our aim is to get only the magnitude. That means we just need to multiply the field value with the distance between the plates. We can see that the value of electric field, potential between the plates, will be equal to sigma by epsilon 0 times, what is the distance? We mentioned the distance as is equal to d. So I got the inputs for finding out the value of capacity. I got the Q value, I got the V value. Substituting into this expression, we will get the value of capacity as C is equal to Q by V. What is Q? Q is sigma A. So that is sigma times A over, what is V? V is sigma by epsilon 0 into D. So we can write sigma d by epsilon 0. Sigma cancels. That means it is independent of the charges concentrated on the plates. Rearranging, I'll get epsilon 0 A divided by D as the expression for the capacity of a parallel plate capacitor. You can see that even though the capacity is relating the charge to voltage ratio, ultimately we got the expression as C is equal to epsilon naught A divided by D. That means the capacity of the parallel plate capacitor depends only on the physical arrangement of the parallel plate capacitor. It is independent of the charges, it is independent of the voltage. It depends only on area of the plate as A, distance between the plates, and the medium in between the plates. So our aim, what I told you is, our aim is always to increase the capacity. What are the different possibilities to increase the capacities? You can see that capacity can be increased by either increasing the area or decreasing the distance between the plates. But physical arrangements of a system has got its own limits. Increasing the area, if you try to increase the area of the capacitor to a very big value, what will happen? The size of the capacitor will keep on increasing. But that is not desirable. In any electrical circuit or in any modern technology, you always require materials or devices with smaller sizes. So area increasal is not a desirable factor to use increasing in capacity. The next possibility is quite acceptable. What is that? You can decrease the distance between the plates to a minimum value which is possible. So that is quite acceptable. But is there any other way to increase that? Obviously there is, because you can see that it is dependent on which one? It depends on epsilon 0, or it depends on the permittivity of the medium. So if I fill this area with a medium with very high value of dielectrics, what will happen? The capacity will increase. That means earlier I have chosen this capacitor with air. I will call this one as a capacitor with air, or air filled capacitor. Rather, if I fill that one with a dielectric of dielectric constant K, I can call that one as a dielectric capacitor. That is our point what I am discussing. I am discussing capacitors and dielectrics. So what will happen for the capacity value? Of course, the value of permittivity in between will increase into K times epsilon 0. Capacity of the dielectric capacitor will become, expression changes as K epsilon 0 A divided by D. If the K value is greater than 1 or maybe equal to 2, what I can say? Dielectric capacitor's capacity is equal to K times capacity of the same arrangement with air. So this is an easy way to increase the capacity because dielectrics are quite available. You can fill that one and you can get the value of capacity to a higher value. Let us see different situations in which the area between the plates of the capacitor is filled by dielectric in different manners. These are three different manners you can fill dielectric medium in between the plates. So the first one, you can see that two dielectrics are used and it is filled in such a way that half of the area is filled with one dielectric and the second half is filled with second dielectric. Let us analyze this problem, then we will move into the next one. I can see that this has got a peculiar nature, this area. We can say that this much area is, if the total area is A, this much area will be equal to A by 2. And distance between the plates is still is equal to D. Or we can say that I have divided the total area into two halves using two dielectrics. I will call this area with a capacity C1 and this area with a capacity C2. What about C1? C1 can be written as K1 into epsilon naught and area between the plates is A by 2 and the distance is D. If the initial capacity is taken as without dielectric is equal to C, then I can write this one as K1 by 2 into C, because C is equal to epsilon 0 A divided by D. In a fashion, if I proceed for the bottom half, C2 can be written as K2 epsilon naught A divided by 2D, that will be equal to K2 by 2 into C. So what we can observe, the situation is just like one capacitance with K1 by 2C and the other one with K2 by 2C. And how they are connected? This is one terminal and this is another terminal. This terminal is connected to first capacitor as well as second capacitor. And this terminal is also connected to first and second. Or I can call this one as a parallel combination of the two capacitances. How and why parallel? Because both the terminals are common to both the capacitor. This is connected to this terminal as well as this. So this is just like one connection here and one connection here. This is also similar to one connection here and one connection here. It's a parallel combination of two capacitances. Now our aim is to get a total capacity or the effective capacity. What will be the total capacity in parallel connection? Parallel connection gives C1 plus C2. So the value is C1 plus C2. Expression becomes very simple. We have got K1 by 2C and K2 by 2C. This is K1 plus K2 whole divided by 2 times C. This is the net capacity if the dielectrics are filled like that. So if I call this one as a capacitance with K into C equal to K1 plus K2 divided by 2 into C, I can say that the net dielectric constant between the plates is equal to what? K1 plus K2 divided by 2. So the filling gives an effective dielectric constant value of K1 plus K2 by 2 and the capacity is C. So this is the net value when the dielectrics are arranged in that fashion. If the arrangement is like this, second arrangement, we have got two dielectrics filling the medium in such a way that the distance between the plates is becoming half for each. So this is D by 2 and this is also D by 2. Say if the initial capacity is epsilon 0 A divided by D, say I can consider this one as a capacitance with C1 value and this one as C2 values. What will be the value of C1? C1 will be K1 epsilon 0. A is same for both. A divided by D by 2. Or this becomes 2 K1 epsilon 0 A divided by D. Or I can say 2 K1 C. Similar, C2 can be K2 epsilon 0 A divided by D by 2 becomes 2 K2 C. Look at the arrangement, how they are connected. This terminal is connected to this plate and that is not connected to the second one. And the second plate of the first capacitor is connected to the first plate of the second capacitor. So this kind of connection is known as a series connection. So this is a series connection and this is a parallel connection. And series connection of two capacitances, what will be the effective value? Effective value is 1 by C is equal to 1 by C1 plus 1 by C2. So 1 by C is equal to 1 by C1. There are two common factors, 1 by 2C is common, 1 by K1 plus 1 by K2. I am taking this side for solving. So 1 by C is equal to 1 by 2C, cross multiplying, this will become K1 plus K2 divided by K1 K2. Taking the reverse, this is the effective value. This is the effective value. Effective value. C effective becomes 2C K1 K2 divided by K1 plus K2. Or how it got altered, we can say C effective is just like a new dielectric with this much value is introduced and the initial capacity. So what is the effective value of the dielectrics? Effective value of the dielectric constant is 2 K1 K2 divided by K1 plus K2. That is the way to solve the problem if it is like this. So the C effective I can write it as 2 K1 K2 divided by K1 plus K2 multiplied by C. That's the way to solve this problem. Now we are into the third situation, in which we can say that the dielectric slab is having a thickness, say T, which is less than what? Less than the total thickness of the dielectric capacitor. Or a small slab is introduced. A small slab is introduced into the plates. So if there is nothing, we will consider it has got this much value. Now what is happening? If a slab is introduced, T part is filled with, say, dielectric constant of K. The remaining part is, this part is air and this part is also air or vacuum, whatever you consider. Okay, so we have got two specific areas. So we can say that the potential in that two different areas have to be analyzed. So we can say that the potential, the total potential difference will be equal to sum of the potential, one potential in air plus potential in dielectric. What is the length of air part? Length of air part is D minus T. And what is that electric field in that area? We can say that that is equal to sigma by epsilon 0. What about the next area? Next area is with electric field sigma by K epsilon 0 into the thickness of the plate. Thickness of the plate. I got the expression for which one? I got the expression for the potential. So what is the capacity? Capacitance is defined as Q by V. What is Q? Q is sigma A. V is, we take the common factor, sigma by epsilon 0 is common. What is remaining within the bracket? First one has got d minus t, second one has got t by k. Sigma cancels. What's remaining? Expression is, we get epsilon 0 a divided by d minus t plus t by k. This is the capacity when a thin slab of thickness T with dielectric constant K is introduced between the plates. So this is the way to find the role of dielectrics or dielectric slab in a capacitor. So why the dielectric is used in a capacitor? The role of dielectric is to increase the value of the capacity. Okay? So we have seen three different situations as parallel, series and partial. So keep all these in your mind, and I hope the capacitance with dielectric will be very clear if you have got this much idea in your mind. Thank you for watching, and keep watching to see the problems based on capacitance which will be relevant for your entrance exams as well as board exams. Thank you. Thank you.